Tonight, we're going to talk about the fact that the most famous object in the solar system is temporary, and that nobody can agree on how it got there. You know what Saturn looks like. It is the one planet a child can draw and everybody recognizes. It is on book covers and school posters and the side of vans. And it is falling apart. Right now, tonight, material is draining out of those rings and into the planet at a rate that has been measured, and at that rate the rings have somewhere between 100 and 300 million years left. That much is not seriously disputed. What is disputed, and disputed sharply, is the other end of the story. For about 6 years the field had what looked like a clean answer. The rings were young, far younger than Saturn, younger than the dinosaurs. That answer was built on a specific measurement, and it was widely reported. In the last 2 years that answer has been taken apart, not overturned exactly, but undermined at the foundation, by people arguing that the clock everybody was reading was never a clock at all. So here is the honest position. We know Saturn's rings are going away. We do not know when they arrived, and the gap between those two statements is where tonight's video lives. By the end you will know what the rings are actually made of, which is stranger than it sounds. You will know how they were weighed, which took a spacecraft flying somewhere nobody had ever flown. You will know both sides of the age argument, properly, including the part that was published this year and has not reached the popular coverage yet. And you will know about a moon that may have been destroyed to make them, which would explain something about Saturn that has puzzled people for a century. 10 sections. Each one stands on its own. If you drift off in the middle of section 4, you will lose nothing you need for section 5. Everything measured will be called a measurement. Everything calculated will be called a calculation. And where the field genuinely disagrees, I will give you both sides rather than the tidier one. Before we begin, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with what the rings are, because almost everybody gets this wrong in the same specific way. They are not solid, they are not a disk, they are not a sheet of anything. They are individual objects, each one in its own orbit around Saturn, going around the planet independently, the way a moon does. There are somewhere in the order of hundreds of trillions of them, and the great majority are ice, not rock with ice on it, not dirty ice, water ice at a purity above 99%, which is cleaner than almost anything on the surface of this planet. That number is the beginning of the whole mystery, and we will come back to it in section 5, but hold on to it. The rings are made of nearly pure water ice. The individual pieces run across an enormous range of sizes. The smallest are dust grains you would need a microscope to resolve. The largest are the size of a house, and in places, the size of a small mountain. The typical piece, the one that carries most of the mass, is somewhere around the size of a snowball or a boulder, so the structure is a swarm. Hundreds of trillions of lumps of ice, ranging from dust to mountains, each on its own path. One consequence of that size range is worth stating, because the density is not what the photographs suggest. The rings are mostly empty space. Even in the densest part of the B ring, the particles are separated by distances comparable to their own sizes or larger. If you took a cubic mile of the B ring, the great majority of it would be vacuum with lumps of ice scattered through. That is why you can see stars through the rings. Cassini used exactly that, watching stars pass behind the rings and measuring how the light flickered, to work out how much material was in each region. The rings look solid for the same reason a cloud looks solid. Enough scattered objects, viewed across enough distance, and the gaps stop being visible. Now the dimensions, because this is where it stops sounding like anything on Earth. Measured from the outer edge on one side, across the planet, to the outer edge on the other, the main ring system is about 170,000 miles wide. That is more than 2/3 of the distance from the Earth to the Moon. If you put Saturn where the Earth is, the rings would fill most of the way to the Moon, and the thickness in most places is about 30 feet. Read those two numbers next to each other again. Something 170,000 miles across and 30 feet thick. In some regions, the main rings reach a few hundred feet, and at the very edges there are structures a mile or two high where a moon is disturbing them. But the ordinary thickness of the ordinary ring is about the height of a 3-story building. Here is the ratio, cashed out. If the ring system were shrunk down until it was the length of a football field, it would be roughly 30 times thinner than a sheet of paper. There is nothing else in the solar system with that shape. Nothing is that wide and that flat. Why it is that flat is worth one paragraph, because it is not an accident and it is not decoration. Anything orbiting Saturn on a tilted path crosses the ring plane twice per orbit. When it does, it hits things. Collisions cancel out motion above and below the plane, because that is the component that produces the impact, while motion around the planet is untouched. Run that for long enough and every surviving particle ends up in the same plane, moving the same direction. The rings are flat because everything that was not flat got hit until it was. That process also tells you the collisions are gentle. If the pieces were slamming into each other at high speed, they would shatter and grind down to powder. Instead, particles in the same region of the rings are moving at nearly the same speed, and they meet at a walking pace or slower. They bump, they nudge, sometimes they stick together briefly and pull apart again. There is a consequence of that gentleness which is worth stating, because it changes what the rings actually are on a moment-to-moment basis. Ring particles are not permanent objects. They are constantly sticking together and coming apart. Two lumps of ice meeting at walking pace can stay together, held by their own faint gravity, forming a temporary aggregate. Then the shearing motion of the rings pulls the aggregate apart again, or another impact breaks it. Estimates for how long a given clump survives before being disrupted run from hours to days in the denser regions. So the ring particle you would photograph is not a rock that has been there since the rings formed. It is a temporary assembly, one of a population that is continuously being built and dismantled. The mass is conserved, the objects are not. That matters for Section 6, because a system that is constantly turning its own material over is a system whose surfaces are constantly being renewed, and surface renewal is exactly what an exposure age measurement is sensitive to. Now the layout, because the rings are not one thing, they are a set of named regions, and the names are worth knowing because they come up constantly in what follows. Working outward from Saturn, the D ring is innermost, faint, close to the cloud tops, then the C ring, sometimes called the crepe ring because it is dim enough to see the planet through it, then the B ring, which is the bright one. When you look at a picture of Saturn, the wide, brilliant band that dominates the image is the B ring. It holds most of the mass of the entire system. Then a gap, about 3,000 miles wide, called the Cassini division. That gap is dark in photographs, and it is the single most obvious feature in the rings after the rings themselves. It is not empty, but it is thin enough to look empty. Section 9 explains what put it there, and the answer is a moon. Then the A ring, the outer bright ring, which has its own narrower gaps inside it. Then the F ring, a thin twisted strand just outside the A ring, kept in place by two small moons. And then, much further out and far fainter, the G ring and the E ring, which are diffuse enough that you would never notice them in an ordinary photograph. Two of those names are worth explaining, because the lettering looks arbitrary, and it is. The rings were not named in order of position, they were named in order of discovery. A and B were the two obvious bright rings known since the 1600s. C was the faint one found in 1850. D, E, F and G came later, as fainter structures turned up. So the sequence outward from the planet runs D, C, B, A, F, G, E, which is not alphabetical and never was. It is the order in which people notice things, laid out in space. If you have ever looked at a ring diagram and assumed you were missing something, you were not. The labeling is a historical accident that nobody has bothered to fix. The E-ring is worth flagging now because of where its material comes from. It is being continuously resupplied by ice erupting from the south pole of the moon, Enceladus. That is a measured fact, not a theory, and it is section 9. One more property, and it is the one that makes the rings behave the way they do. They are not turning as a unit. Every particle obeys the same rule, every orbiting object obeys, which is that closer means faster. A particle at the inner edge of the main rings goes around Saturn in about 5.5 hours. A particle at the outer edge of the A-ring takes about 14 hours. So the inner rings are constantly overtaking the outer rings, and material at different radii is permanently sliding past material next to it. That shearing motion is why the rings have structure at all. Every gap, every wave, every sharp edge you can see in a Cassini photograph exists because something is disturbing a system that is sliding against itself. There is a detail about how we know the rings are ice that is worth having, because you might reasonably ask how anybody establishes the chemistry of something 800 million miles away. The method is spectroscopy, and it works because every material absorbs light at its own particular set of wavelengths. Water ice has a distinctive absorption pattern in the near-infrared. Point an instrument at the rings, spread the reflected sunlight out by wavelength, and if water ice is there, specific bands go dark in a specific arrangement. That measurement was made from the ground in the 1970s, well before any spacecraft arrived, and the answer came back immediately and unambiguously. The bands were there, and they were deep, meaning not a trace of ice but a surface made of it. What spacecraft added later was precision about how much of anything else is present, and the answer to that is very little. Depending on the region, the non-icy fraction runs from a few percent down to a fraction of 1%. Hold on to that too. It is the single most important number in tonight's video, and sections 5 and 6 are both arguments about it. The temperature is worth one line as well. Ring particles sit between about -240 and -330 degrees Fahrenheit, varying with how much sunlight they are getting and whether they are in Saturn's shadow. At those temperatures, water ice is not slushy or soft, it behaves like rock. There is one more structural feature, and it was only confirmed by Cassini. The rings are not evenly spread, even at small scales. Within the dense regions, particles clump together into elongated groups, held loosely by their own gravity, constantly forming and being pulled apart again by the shearing motion. These are called self-gravity wakes. They are tilted at a consistent angle to the direction of orbit, and they are the reason the rings look different depending on which side you view them from. What had been assumed to be a smooth sheet turns out to be a fine-scale texture of gravitational clumps, forming and dissolving on timescales of hours. Now the total, which is the number that ends this section and sets up section 4. Add up every piece of ice in every ring, and the entire system weighs about 15 quintillion tons. Written out, that is 15, followed by 18 zeros. That sounds enormous. It is not. Saturn's moon Mimas is one of the smaller round moons in the solar system, about 250 miles across, and not a body anybody thinks about much. The entire ring system, all 170,000 miles of it, weighs less than half of Mimas. Spread out, it is spectacular. It would make an unremarkable moon. And that number, the mass, is the number the whole age argument turns on. It was not measured until 2017, and getting it required flying a spacecraft through a gap nobody had ever flown through. That is the first section. The rings are hundreds of trillions of separate pieces of nearly pure water ice, spread 170,000 miles wide and 30 feet thick, sorted into named bands, sliding past each other and weighing less than half of a moon most people have never heard of. Nobody knew what they were looking at for 45 years. That is the second section. and it is worth your time for a reason that goes beyond history. The story of how the rings were figured out is also the story of how you find out what something is when you cannot go there, which is the only method anybody had for almost all of astronomy. It starts in 1610. Galileo Galilei turned a telescope on Saturn in July of that year. His instrument magnified about 20 times, which is less than a pair of modern binoculars, and the image was blurred and coloured at the edges. What he saw was not a ring. He described Saturn as 3 bodies, a large one in the middle with 2 smaller ones touching it on either side. He wrote that Saturn had ears. He was confident enough to announce it, and he did what natural philosophers did at the time, which was to publish it as a scrambled anagram so that he could claim priority later without giving the discovery away. Decoded, it said that he had observed the highest planet to be triple. Then, in 1612, the ears vanished. Galileo looked again, and Saturn was a plain disk. Nothing on either side. He had no explanation, and what he wrote about it is one of the more human moments in the history of astronomy. He asked whether Saturn had devoured its own children. The ears came back a couple of years later, and then they changed shape, and he never resolved it. He died in 1642 without knowing what he had seen. You should sit with that for a second, because it is easy to read past. The man who found the moons of Jupiter, who worked out how falling bodies accelerate, who was tried by the Inquisition for what he saw through a telescope, spent 30 years unable to explain a thing he had looked at directly and drawn. He was not being slow. He simply had no way to know what he was missing. Here is what was actually happening, and it is a piece of geometry rather than a mystery. Saturn is tilted at about 27 degrees, in much the same way the Earth is tilted. The rings sit around its equator, so they share that tilt. As Saturn goes around the Sun, which takes about 29.5 Earth years, we see the rings from changing angles. Twice per Saturn year, we pass through the ring plane exactly. At that moment, we are looking at the rings edge on, and a structure 30 feet thick seen from 800 million miles away is not visible in any telescope. The rings do not fade. They disappear completely. That is what happened in 1612. Galileo had the bad luck to make his discovery 2 years before a ring plane crossing. Those crossings still happen. The most recent was in 2025, and for a period around it, telescopes on Earth saw Saturn without rings, exactly as Galileo did. The next one after that is in 2038. So the disappearing act is not history. It is a thing you can go and observe. Before the answer, it is worth appreciating how badly people were guessing in between, because you can only judge Huygens properly against what he was competing with. Proposals published in that period included Saturn having 2 large moons permanently attached to its sides, Saturn being egg-shaped, Saturn having handles, and Saturn having 2 dark arms that swung around it. One astronomer drew it with 2 crescent shapes facing outward. Another drew it as a disk with 2 loops like the ears of a jug. None of them worked because none of them explained the disappearance. Any solid attachment should still be visible when seen from a different angle. A shape that vanishes entirely and comes back is a very specific constraint, and everybody kept proposing things that would not do that. The answer came in 1655 from a Dutch astronomer named Christian Huygens. Huygens had 2 advantages. The first was a better telescope, which he and his brother built themselves, and which magnified about 50 times. The second, and it mattered more, was that he ground his own lenses to a standard nobody else had reached. He watched Saturn across several years, which meant he watched the shape change through more than one phase, and he worked out that a single explanation covered every appearance anybody had recorded. Saturn was surrounded by a thin, flat ring, touching nowhere, tilted with respect to us. That was it. 1 sentence, and 45 years of confusion resolved. He published it the same way Galileo had, as an anagram, in a pamphlet in 1656, and gave the solution 3 years later in a book called Systema Saturnium. If you want a sense of what that took, consider that Huygens had no photograph to study, no way to record what he saw except by drawing it, and no ability to observe on a cloudy night or in daylight. He had his own eye at an eyepiece, a notebook, and several years, and the thing he was trying to explain kept changing shape on a schedule nobody had worked out yet, because nobody knew the rings were tilted, because nobody knew there were rings. He was right, and he was also wrong about one detail, and the detail turned out to matter. Huygens thought the ring was solid, a rigid hoop, one object. That assumption stood for 200 years. The next piece came in 1675 from Giovanni Domenico Cassini, an Italian astronomer working at the newly built Paris Observatory. Cassini was looking at Saturn with a long focus telescope, and he noticed a dark line running around the ring, dividing it into two, an inner bright section and an outer one, with a gap between them. That gap carries his name. It is the Cassini division, and it is the feature described in section 1, about 3,000 miles across. The significance was not the gap itself. It was what a gap implies. A solid, rigid hoop does not have a slot cut out of it for no reason. Cassini said so directly. He suggested the ring might be made of a great number of small particles, too small to see individually, and that what looked continuous was actually a crowd. He was right, in 1675, with no way to prove it. And you will notice that nobody acted on it for the better part of 2 centuries, because a correct guess with no supporting argument does not move a field. It just sits there being correct. Proof took another 184 years, and it did not come from a telescope, it came from mathematics. In 1855, the University of Cambridge set its Adams Prize competition on the subject of the stability of Saturn's rings. The question was straightforward to state: what could the rings be made of such that they would not fall apart? James Clerk Maxwell, then in his mid-20s, worked on it for 2 years and submitted the only entry. What he did was test each possible answer to destruction. A solid, rigid ring, he showed, cannot survive. Saturn's gravity pulls harder on the near side of such a ring than the far side, and any tiny displacement gets amplified rather than corrected. The ring would not wobble and settle. It would drift off center, accelerate, and crash into the planet. He calculated that such a ring could only be stable if its mass were distributed in a way so lopsided it was physically absurd. A liquid ring, he showed, fails differently. Waves would grow along it until it broke into blobs, and the blobs would collide and destroy themselves. That left one answer. The rings had to be composed of an indefinite number of unconnected particles, each orbiting independently, and the appearance of solidity had to be an illusion of distance. He submitted it in 1857 and won. The essay was published in 1859. It is one of the cleanest examples in physics of somebody establishing what an object is made of without observing it, purely by ruling out every alternative. Maxwell never saw a ring particle. He proved they had to exist. The observational confirmation arrived in 1895. James Keeler, working at the Allegheny Observatory in Pittsburgh, used a spectrograph to measure how fast different parts of the ring were moving. The technique is the same one used today to find planets around other stars. Light from an object moving toward you is shifted slightly toward blue, and light from an object moving away is shifted toward red, and the size of the shift gives the speed. If the rings were a solid hoop, the outer edge would be moving faster than the inner edge, because it has further to travel in the same rotation. Keeler measured the opposite. The inner edge was moving faster. That is the signature of independent orbits, and it is exactly what Maxwell's mathematics required. Every particle was going around Saturn on its own, obeying the same rule as a moon. 285 years after Galileo saw ears, the rings were understood. 2 things happened between Cassini and Maxwell that are worth adding, because they show how slowly this subject moved when the only tool was a telescope. In 1789, William Herschel measured the thickness of the rings and concluded they were extremely thin. He could not say how thin, only that the rings vanished at plane crossing and therefore had to be far thinner than anything else anybody was measuring. He also correctly identified that the rings rotate. Then in 1850, two teams independently found a third ring. William Bond and his son George, working at Harvard, and William Lassell in England, all noticed a faint dusky band inside the two known bright rings. It is so dim that you can see Saturn's disk through it, which is why it was called the crepe ring, after the semi-transparent fabric. That ring is the C ring from section 1, and the fact that it took 240 years to notice something that large tells you how hard this subject was before spacecraft. It also mattered for a different reason. A ring you can see through is a ring that cannot be solid, and the Bonds said so at the time. The evidence against Huygens' rigid hoop was accumulating from several directions before Maxwell finished it off. Then nothing much happened for 80 years, because there was nothing more to learn from Earth. The rings were too far away and too thin. Pioneer 11 flew past Saturn in September of 1979, the first spacecraft ever to do so, and returned images that were a real improvement on anything from the ground and still nowhere near enough. Pioneer 11 is worth one more sentence, because of what it was actually for. It flew through the ring plane deliberately, outside the main rings, partly to find out whether a spacecraft could survive doing that. The answer was yes, and that result is why the Voyagers were allowed to plan the trajectories they did. Voyager 1 arrived in November of 1980. Voyager 2 followed in August of 1981. What those two spacecraft sent back reset the subject completely. The rings were not a handful of bands, they were resolved into thousands of individual ringlets, with sharp edges, waves, braided strands and gaps that had never been suspected. One of the Voyager scientists described the images as showing a phonograph record. They also found something nobody had predicted at all, which was dark radial streaks appearing and disappearing across the B-ring. Those are the spokes, and they are section 10, and they are still not fully explained 45 years later. A word about the naming, because it causes confusion, and you are going to hear both used tonight. Giovanni Cassini, the 17th century astronomer, has a gap named after him, the Cassini division. The spacecraft, launched 320 years later, was named after the same man. So when you hear that Cassini photographed the Cassini division, that is a spacecraft named after an astronomer photographing a gap named after the same astronomer, 3 centuries after he found it with a telescope from a garden in Paris. The full name of the mission was Cassini-Huygens, because it carried a probe that separated and landed on Titan in January of 2005. That probe was named after Huygens, who worked out what the rings were, and who also discovered Titan in the same year, 1655. 2 men who between them solved Saturn in the 1650s, and their names went back there together on the same vehicle. And then Cassini, which is the spacecraft that produced almost every number in this video. It launched in October of 1997, took nearly 7 years to get there, and entered orbit around Saturn in July of 2004. It stayed for 13 years. 13 years is the detail that matters. Saturn's year is 29.5 hours, so Cassini was there for close to half a Saturn year, which meant it watched the rings through a full change of season and lighting. Almost everything we know about how the rings change over time comes from that one mission having stayed long enough to see change. That is the second section. Galileo saw ears and could not explain them. Huygens worked out it was a ring. Cassini found the gap and guessed it was particles. Maxwell proved it had to be particles by eliminating everything else. Keeler measured it. And then the spacecraft arrived and found that the real structure was more complicated than any of them had imagined. Every giant planet in this solar system has rings. You have probably never seen 3 of them. Jupiter has rings. Uranus has rings. Neptune has rings. All three were confirmed within about 15 years of each other, and not one of them is visible in an ordinary photograph. So the question in this section is not why Saturn has rings. It is why Saturns are the only ones you can see, and whether that is a fact about Saturn or a fact about timing. You have almost certainly seen an image of Jupiter's rings without registering it, because they only show up in particular lighting, and they look like a haze rather than a structure. And you have very likely never seen an image of Neptune's at all. That is not a gap in your knowledge. It is a fact about how faint they are. If you took the best photograph of Saturn you have ever seen and put Uranus's rings into it at their true brightness, you would not be able to find them. Start with why rings exist anywhere, because there is a specific distance involved and it has a name. Any moon orbiting a planet is being pulled on unevenly. The side facing the planet is closer, so it is pulled harder. The far side is further, so it is pulled less. The difference between those two pulls tries to stretch the moon along the line pointing at the planet. Holding the moon together against that stretch is its own gravity. Far from the planet, the moon's own gravity wins easily and nothing happens. Move the moon closer, and the stretching force grows, and it grows fast, because it scales with the cube of the distance. Halve the distance and the stretch goes up eightfold. At some distance, the stretch matches what the moon's gravity can resist. Inside that distance, a body held together only by its own gravity comes apart. That distance is called the Roche limit, after Édouard Roche, the French astronomer who worked it out in 1848. For Saturn, the Roche limit for an icy body sits at roughly 87,000 miles from the planet's center. Now look at where the rings are. The main rings run out to about 85,000 miles. They end, almost exactly, at the Roche limit. That is not a coincidence, and it is the cleanest single explanation of the whole system. Inside that line, ice cannot gather into a moon. Every time two pieces drift together and start to stick, Saturn pulls them apart again. Outside that line, material clumps, and Saturn has more than 100 moons. So the rings are the material that is too close in to be allowed to become a moon. You can apply that rule to yourself, which is the quickest way to see why size matters here. Your body holds together by chemical bonds, not by gravity. Your own gravitational self-attraction is far too weak to be relevant to anything about you. So the Roche limit does not apply to you at all, and you could sit well inside Saturn's without being pulled apart by tides. Whereas a moon, 900 miles across, is held together by gravity and almost nothing else, which is exactly why it cannot survive there. One caution, because the Roche limit is often stated too strongly. It applies to a body held together purely by gravity. Something small enough that its own physical strength matters. A boulder, an ice block, a snowball can sit well inside the Roche limit and be perfectly fine. That is why individual ring particles are stable, while a large moon in the same place would not be. The limit is not a shredder. It is a rule about assembly. It says a big object cannot form there, not that every object there gets destroyed. There is a consequence of the Roche limit that applies closer to home and that you may not have connected to Saturn. Mars has two small moons. Phobos, the inner one, orbits about 6,000 miles above the surface, and it is spiraling inward, losing about 6 feet of altitude per century. Mars's Roche limit for a body like Phobos sits somewhere around 4,000 miles out. So in roughly 30 to 50 million years, Phobos reaches the line, and the same thing that Section 7 proposes happened at Saturn happens at Mars. The modelling suggests Phobos is weak enough and already fractured enough that it will not survive. A portion will impact the surface, the rest is expected to spread into a ring. Mars is going to get rings, not large ones, and not for tens of millions of years, but the physics is the same physics, and the object doing it is already on its way in. That is a useful thing to hold, because it means ring formation is not a freak event confined to the distant past. There is one queued up in this solar system right now. Now the other 3 planets. Jupiter's rings were discovered in March of 1979 by Voyager 1, and they were not expected. The imaging team took a long exposure of the region near the planet, mostly to check, and there was a faint band. They are almost entirely dust, fine particles, most of them smaller than the width of a human hair, and there is very little water ice in them. They are also faint to a degree that is hard to convey. Jupiter's main ring reflects so little light that it took a spacecraft to confirm it existed at all, from a planet we have been staring at through telescopes for 400 years. Where that dust comes from is understood, and it is the interesting part. 4 small inner moons, Metis, Adrastea, Amalthea, and Thebe, are being continuously hit by micrometeoroids. Each impact knocks dust off the surface, and because those moons are small, their gravity is too weak to hold the dust down. It escapes into orbit and becomes the ring. So Jupiter's rings are not the remains of anything. They are a permanent haze of debris being resupplied from 4 moons, and if those moons stopped being hit, the rings would clear out in a few thousand years. There is a second thing at Jupiter worth knowing, because it is the closest thing anybody has watched to a ring-forming event. In July of 1994, a comet called Shoemaker-Levy 9 struck Jupiter. It had been captured into orbit around the planet years earlier, and on a previous close pass, it had crossed inside Jupiter's Roche limit and been torn into more than 20 fragments. Astronomers photographed the fragments strung out in a line before the impacts, and the string was described at the time as a string of pearls. That is the Roche limit, doing exactly what Section 7 proposes happened at Saturn, observed live in the 20th century by anybody with a telescope. The difference is what happened next. The fragments were on an orbit that took them into the planet rather than into a stable ring, so instead of spreading into a disk, they hit Jupiter one after another over 6 days, leaving dark scars in the atmosphere larger than the Earth. So the tidal disruption is not a theoretical process. It has been watched. Whether the debris becomes a ring or becomes an impact depends entirely on the orbit it is left on. Uranus is different again. Its rings were discovered in March of 1977, and by accident, a team was flying an infrared telescope aboard a converted aircraft, the Kuiper Airborne Observatory, to watch Uranus pass in front of a star. That kind of event, called an occultation, lets you measure a planet's diameter and probe its atmosphere very precisely. The star blinked out 5 times before Uranus reached it. Then, after the planet had passed, it blinked out 5 more times, symmetrically, on the other side. Rings, narrow dark ones, invisible in any image available at the time. There are 13 known now. They are narrow, some only a few miles wide, and they are extremely dark. The material reflects about as much light as charcoal, which is why nobody saw them. Something in them, probably radiation-processed organic material, has been darkened over time. There is a thing about that discovery you should hold on to, because it is the same technique that keeps coming up tonight. Watching a star blink out behind an object tells you an enormous amount, and it costs nothing but timing. It gave us Uranus's rings, it gave us Chariklos, it gave us Haumeas and Quaoas, and it is how the sizes of most distant solar system objects are known. You do not need a spacecraft. You need to know exactly when the light stopped and exactly when it came back, from several places at once. Neptune's rings were confirmed by Voyager 2 in August of 1989, and they have a genuinely odd feature. The outer ring is not uniform. It contains several dense arcs, clumps of material that stay clumped instead of spreading out around the ring as they should. They are named Liberté, Égalité, Fraternité and Courage. What holds them together is still argued about, with the leading explanation involving the moon Galatea. Chariklo is worth a little more, because the discovery is a good story, and because of what it forced people to accept. The observation was made in June of 2013, from several sites in South America, watching Chrysalis pass in front of a star. The team was after the object's size and shape, which is the ordinary reason to observe an occultation. The star blinked twice before Chrysalis covered it, and twice again afterward. Two narrow rings, about 4 miles and 2 miles wide, separated by a gap of about 5 miles. That is a ring system you could walk across in an afternoon, around an object with so little gravity that a person could throw a ball off it into space. The awkward part is keeping it there. Narrow rings spread out unless something confines them, which around a planet means shepherd moons. Around a 155-mile object, there was no obvious candidate, and the search for one has not produced a confident answer. Rings were then found around Haumea, a dwarf planet out beyond Neptune in 2017, and around Quaoar in 2023, in a position that made the result genuinely awkward, because Quaoar's ring sits well outside its Roche limit, where the material should have gathered into a moon and did not. You may have noticed something about all three of those discoveries. Jupiter's rings were found by a spacecraft that went to look at something else. Uranus's were found by a team measuring the planet's diameter. Neptune's were confirmed on a flyby. Not one of them was found by somebody looking for rings, because nobody expected to find any. For 360 years, the working assumption was that Saturn was the planet with rings, and the others were not that kind of object. That assumption fell apart entirely between 1977 and 1989, in 12 years, and it fell apart because instruments got good enough, rather than because anybody had a new idea. So the pattern across all four is this: every giant planet has rings. 3 of them have faint, dusty, dark ones with very little ice. One of them has an enormous, brilliant, nearly pure ice system. Saturn is not the planet with rings. Saturn is the planet with a ring system that is different in kind from the others by a factor of somewhere around 1 million in mass. Why is the whole question of this video? And there are only 2 possible shapes of answer. Either something about Saturn specifically makes it able to build and keep a large ring system, in which case the rings can be ancient and the other planets simply never had the chance. Or Saturn got lucky recently. Something happened there in the geologically recent past that did not happen at Jupiter or Uranus or Neptune, and we are looking at a temporary state that those planets may have passed through at some point when nobody was watching. Those 2 answers make different predictions, and they are what sections 5 and 6 are about. There is a third thing worth putting on the table now, because it does not fit either box neatly, and it is one of the more interesting results of the last decade. Rings are not restricted to planets. In 2013, a team watching a small object in the outer solar system pass in front of a star saw the same blink pattern that gave away Uranus. The object was Chrysalis, which is about 155 miles across and orbits between Saturn and Uranus. Chrysalis has 2 narrow rings. An object with about 1/200th of Earth's diameter has a ring system. Nobody predicted that, and the models of how rings form and survive had to accommodate it afterward rather than before. The Quaoar result is unresolved. There are proposed explanations involving the ring particles being unusually bouncy, or a resonance keeping them stirred up, and none of them is settled. So the honest state of the field on rings in general is that they are more common than anybody expected. They appear around objects far too small to have been considered candidates, and at least one of them is in a place the standard theory says it should not be. That is the third section. Rings form inside the Roche limit, where a moon cannot assemble, and Saturn's main rings end almost exactly at that line. All 4 giant planets have them. Only Saturn's are made of clean ice, and only Saturn's are massive enough to see, and whether that is a permanent fact about Saturn, or an accident of what century we happen to be looking in, is the argument the rest of tonight is about. To settle how old the rings are, you first have to know how much they weigh. And to weigh them, somebody had to fly a spacecraft into a gap 1,200 miles wide between a planet and its own rings 22 times. That is the fourth section, and it is the single most important measurement in this video. Start with why the mass matters, because if you do not have that, the rest of the section is just a spacecraft doing something dangerous for no stated reason. The rings are being polluted. Dust from the outer solar system falls into the Saturn system continuously, and that dust is dark and rocky, and the rings are bright and icy. Over time, dark material accumulating in bright ice makes it dirtier. Now think about what happens if you change the amount of ice. A small ring system gets dirty quickly, because the same amount of incoming dust is being mixed into less material. A very massive ring system takes far longer to show the same discoloration, because the dust is diluted. So the cleanliness of the rings only tells you their age if you know their mass. Without the mass, the observation that they are clean is compatible with almost anything. That is why the number mattered, and until 2017 nobody had it. Estimates in the literature spanned a factor of several, and the age conclusions that came out of them spanned everything from a few tens of millions of years to the full age of the solar system. So if you take nothing else from this section, take that. The cleanliness of the rings is only evidence about their age, if you know how much ice the dirt is being mixed into. That is the whole reason a spacecraft was flown somewhere dangerous. Now the problem of actually measuring it. You weigh a distant object by watching how it pulls on something else. That is how every mass in astronomy is determined, from a planet to a galaxy. The trouble at Saturn is that the rings sit right next to a planet 95 times the mass of Earth. From anywhere outside the rings, the pull you feel is overwhelmingly the planet, with the rings contributing a tiny correction buried inside it. Every spacecraft that had ever visited, including Cassini for its first 13 years, orbited outside the rings. From there, the two pulls point the same way and cannot be told apart. The only way to separate them is to get between them. Fly inside the innermost ring, and the geometry inverts. The planet is pulling you one way, and the entire ring system is pulling you the other. Now the two signals point in opposite directions, and the ring contribution becomes something you can isolate. There is a 1,200-mile gap between Saturn's cloud tops and the inner edge of the D-ring. That is the only place in the system where that measurement can be made. Nobody had ever flown a spacecraft through it, and there was a real chance it would not survive. Models disagreed about how much material was drifting in that gap, and Cassini would be crossing it at around 76,000 miles per hour. At that speed, a particle the size of a grain of sand carries enough energy to punch through the spacecraft. So the mission planners did the obvious thing, which was to wait until the end. Cassini had been at Saturn since 2004 and was running out of fuel. Once the fuel is gone, you cannot steer, and an uncontrolled spacecraft eventually crashes somewhere. Two of the places it might crash were Enceladus and Titan, both of which have liquid water, and both of which are places anybody would want to search for life without having contaminated them first with hardware from Earth. That constraint decided the ending. The spacecraft had to be destroyed deliberately, on a schedule, while there was still fuel to aim it, which meant the last year could be spent doing things that were too dangerous to attempt at any earlier point, because the spacecraft was going to be destroyed regardless. They called it the grand finale. 22 orbits, from April to September of 2017, each one diving through the gap between the planet and the rings, at altitudes between about 1,600 and 2,400 miles above the cloud tops. For the first pass, the team turned the high-gain antenna forward and used it as a shield, on the reasoning that if something was going to be hit, it might as well be the most robust surface on the vehicle. The gap turned out to be almost empty, cleaner than the models had predicted. After the first crossing, the shielding was dropped and the instruments were pointed at the things they were there for. There is a decision buried in that plan that is worth pulling out, because it is the reason the measurement exists at all. Cassini could have been disposed of cheaply, sending it out of the Saturn system entirely. or parking it in a stable orbit far from the moons would have satisfied the contamination requirement without any risk. Instead, the team spent years designing an ending that would produce science, and accepted that the spacecraft might be destroyed months earlier than planned if the gap turned out to have material in it. That trade was made deliberately. A working spacecraft with a known remaining lifetime was flown into the one place nobody had been, because the alternative was to end the mission, having not made a measurement that could only be made there. Everything in sections 5, 6 and 7 of tonight's video exists because of that decision. Here is how the weighing worked. On 6 of those crossings, a radio link was held open between the spacecraft and the deep space network on Earth. Cassini transmitted a steady tone. As the spacecraft accelerated and decelerated under the gravity of everything around it, the frequency of that tone shifted very slightly. The precision achieved on that measurement is difficult to state without it sounding like an exaggeration. Changes in Cassini's speed were tracked to a small fraction of an inch per second, across a distance of about 900 million miles. That data went to a team led by Luciano Ayes at Sapienza University in Rome, and the result was published in Science in January of 2019. The mass of Saturn's rings is roughly 15 quintillion tons, with an uncertainty of about a third of that, and in the comparison that everybody reached for immediately, 0.41 times the mass of Mimas, less than half a small moon. If you want that in a form you can carry, the entire ring system of Saturn, the thing you can identify from a drawing, weighs less than half of a moon you have never heard of. That is a low number. It is at the low end of what had been considered plausible, and it landed on the young side of the argument the moment it was published. The reasoning runs like this. A ring system that small takes a relatively short time to be visibly polluted by incoming dust. Run the calculation with the measured mass and the estimated infall rate, and the rings come out at somewhere in the range of 10 million to a few hundred million years old. That was the headline in 2019, and it hardened in 2023 when the infall rate was measured directly rather than estimated. Section 5 is that measurement. There is a second argument from the same number that gets less coverage and is worth having, because it is independent of the dust entirely. The rings spread, particles collide, exchange momentum, and the system slowly widens, with material moving outward past the Roche limit and inward toward the planet. That process is understood and can be calculated, and it runs faster for a more massive ring than a less massive one. Work through it backwards from the measured mass, and you find that a much heavier ring system in the past would have spread out to its present state on a timescale of hundreds of millions of years, not billions. The rings appear to be a system caught partway through an evolution that does not take very long. Both of those arguments point the same direction, and for about 5 years the case looked closed. I want to be careful here, because Section 6 is going to take a lot of this apart, and I do not want the reversal to feel like a trick. Nothing about the mass measurement is in doubt. ES and his colleagues measured what they said they measured. The technique is sound, the number has held up, and it is one of the finest pieces of spacecraft science ever done. What is in doubt is the step that comes after. The mass is a fact. Turning a mass and a dust rate into an age requires assumptions about what happens to that dust once it arrives, and those assumptions are what got attacked. There is one more thing about that measurement worth knowing, because it is the kind of detail that gets left out, and it explains why the result took 2 years to publish after the data was collected. The gravitational signal Cassini felt was not just the planet and the rings, it was also the winds. Saturn's atmosphere is not rotating as a solid body. Different latitudes move at different speeds, and moving mass produces its own gravitational signature. To extract the ring mass, the team had to model the planet's interior and its wind structure at the same time, because all three effects are tangled together in the same set of Doppler measurements. That is why the published result carries an uncertainty of about a third. It is not that the tracking was imprecise. The tracking was extraordinary. It is that separating three overlapping signals from one another leaves you with a range rather than a value. You will see the ring mass quoted as a single number in a lot of places. The honest version is 0.41 times Mimas, plus or minus 0.13, and that spread matters when the number is being used to calculate an age. One more thing about the grand finale before the section closes, because it produced results well beyond the rings and they are worth knowing. Cassini measured Saturn's gravity field with enough precision to see inside the planet, the winds, it turns out, and not a surface feature. Saturn's bands extend down about 5,600 miles into the interior, far deeper than anybody expected. The core came out strange as well. Rather than a distinct rocky center with an envelope of gas around it, the data indicate a diffuse region where heavy elements are mixed gradually into the hydrogen over tens of thousands of miles. There is no boundary. The word used in the literature is fuzzy, and the rings themselves gave up structural detail nobody had seen, including textures in the B ring that get described as straw and propellers, which are section 9. The ring images from those final orbits are worth describing, because they are the closest anybody has been and they showed textures that had no names. At the resolution Cassini reached in 2017, features around 500 feet across became visible. That is roughly 100 times better than anything from earlier in the mission. What appeared was structure at every scale the camera could resolve. Clumpy strands were informally called straw. Elongated features were called ropey. There were regions where the material had a grainy quality that nobody had a term for, so the papers ended up using words like these because the standard vocabulary did not cover what was there. That is a real result rather than a curiosity. It means the rings have organization well below the scale anybody had modeled, which constrains how the particles are behaving and how often they collide. It also means that every photograph you have ever seen of Saturn's rings, including the good ones, is smoothing over structure. The mission ended on September 15, 2017. Cassini was put into Saturn's atmosphere deliberately, transmitting until the attitude thrusters could no longer hold the antenna pointed at Earth, which lasted about half a minute longer than predicted. The signal reached Earth 83 minutes after the spacecraft had already been destroyed. That is the fourth section. To find out whether Saturn's rings are young, somebody had to weigh them, and to weigh them a spacecraft had to fly between a planet and its rings 22 times at the end of its life. The answer came back at less than half the mass of Mimas, and that number is what put the young ring theory on the map. If you have heard anything about Saturn's rings in the last few years, you have heard that they are younger than the dinosaurs. This is the section where you find out exactly what that claim rests on. And it rests on one instrument, doing one job, for 13 years. The argument is simple enough to state in 3 sentences, and I want to give it to you cleanly first, because it is a good argument, and it deserves to be presented at its strongest before section 6 comes after it. The rings are made of nearly pure water ice. Dark, rocky dust from the outer solar system is falling into them continuously and should be making them dirty. They are not dirty, therefore they have not been sitting there long. That is the whole case. Everything else is measurement. Start with the dust, because you may be wondering where it comes from. The outer solar system is full of small debris. The Kuiper belt, beyond Neptune, contains an enormous population of icy and rocky bodies, and those bodies collide and grind against each other, producing fine particles. Some of that material spirals inward. Saturn, being large and having strong gravity, sweeps up a share of it. The particles involved are tiny, mostly in the micron range, which is smaller than the width of a human hair. They arrive fast, at speeds in the tens of thousands of miles per hour, and critically, they are dark, silicate and carbon-rich material, of the kind that gives comets and outer solar system objects their sooty appearance. Mix enough of that into clean water ice, and the ice stops looking clean. There is a symmetry here that is worth pointing out and that rarely gets mentioned. The Kuiper belt is both the source of the dust that is supposed to be aging the rings and one of the leading candidate sources for the material the rings are made of. Section 7's main alternative to the Chrysalis moon is a captured Kuiper belt object torn apart on a single pass. So on one version of events, the rings are made of outer solar system material and are being dated by outer solar system material arriving later. That is not a problem for the argument. It is just an odd feature of it, and it means the same population of distant icy bodies is doing two different jobs in the same story. You can sanity check the direction of that argument against something ordinary, and it holds. Snow on the ground near a road turns grey within days. Snow in a field stays white for weeks. Same snow, different amount of incoming dark material, and the difference in appearance is obvious and fast. The rings are the field, and the question is how long the field has been open. Now, the instrument. Cassini carried something called the Cosmic Dust Analyzer. It is not a camera. It is a device that catches individual dust grains and tells you what each one was made of and where it came from. The way it works is worth a moment because it is a nice piece of engineering. A grain arriving at tens of thousands of miles per hour hits a metal target inside the instrument. At that speed, the grain does not bounce or embed. It vaporizes instantly, and so does a small patch of the target, producing a puff of electrically charged fragments. Those fragments are then accelerated down a tube toward a detector. Lighter fragments accelerate faster and arrive first. Heavier ones arrive later. Measuring the arrival times tells you which elements were present. So every grain that goes into the instrument produces a chemical readout of itself, and the direction the spacecraft was pointing tells you where it came from. The instrument was run by a team led originally from the Max Planck Institute, and the ring dust analysis was led by Sascha Kempf at the University of Colorado Boulder. Over 13 years at Saturn, the analyzer collected 163 grains that could be confidently identified as having come from outside the Saturn system rather than from the rings or the moons. 163 grains. 13 years. That is the entire dataset, and it is worth sitting with because it is a good illustration of what deep space measurement actually looks like. Not a flood of data. 163 individual specks, caught one at a time, over more than a decade. From those grains and the known collecting area of the instrument, the team calculated the rate at which outside dust arrives at the ring system. Then they combined that with the ring mass from section 4 and asked how long it would take that infall to dirty the rings to their observed level. The answer, published in Science Advances in May of 2023, was no more than a few 100 million years. The figure usually quoted from that work is 400 million years at the outside, and the analysis allows for considerably less. That is where the dinosaur comparison comes from, and it is worth doing properly because it is usually done badly. The first dinosaurs appear in the fossil record around 230 million years ago. The oldest dinosaurs are therefore older than the upper end of the ring estimate is comfortable with, and comfortably older than the middle of the range. So the honest version of the claim is not that the rings are definitely younger than dinosaurs. It is that the exposure age of the rings and the age of the earliest dinosaurs are in the same ballpark, and if the estimate lands anywhere below 230 million years, which most of the range does, then Saturn had no rings when the first dinosaurs were walking around. The implication people found hardest to absorb is the one about most of Saturn's history. Saturn is about 4.5 billion years old. If the rings are 400 million years old, they have existed for about 9% of the planet's life. For the other 91%, the most recognizable object in the solar system was a plain yellow ball. And there is a further consequence that follows directly and does not get said enough. If the rings are that young, then their existence right now, during the few thousand years in which humans have been looking up and recording what they see, is a coincidence. Not a large one. 9% is not a needle in a haystack, but it does mean that the picture every child draws is a snapshot of a temporary condition, and that a civilization arising on Earth 1 billion years earlier or later would have drawn something else. That is the emotional content of the young ring theory, and it is why the result travelled as far as it did. It is worth putting the number next to some Earth history so it stops being abstract. 400 million years ago, the land on this planet had plants on it, but nothing you would call a forest. The first trees were still developing. There were no flowers, no birds, no mammals. The largest animals on land were arthropods. 230 million years ago, at the lower end of the range, the first dinosaurs appear. The continents were still assembled into a single mass. 100 million years ago, which is the other end of the ring estimate, is the middle of the Cretaceous. Flowering plants are established, dinosaurs are at their peak, and the Atlantic Ocean is a fraction of its current width. Somewhere in that span, if the young theory is right, Saturn acquired the feature it is known for. There is something worth sitting with in that. The rings and complex life on land are roughly contemporaries. Both are recent, both are temporary, and neither was here for most of the solar system's history. There is a piece of context that makes the 163 grains more impressive rather than less, and you should have it before deciding what to make of the number. Those grains were not caught in one place. Cassini was moving through the Saturn system for 13 years on a constantly changing orbit, and the instrument had to distinguish grains arriving from outside the system from the vastly larger population of grains produced inside it. The Saturn system is full of its own dust. Enceladus is throwing out ice continuously. The rings are shedding fine particles, and the other moons are being chipped at by impacts. All of that is local material. An interplanetary grain is told apart by two things: its composition, which is silicate and carbon-rich rather than icy, and its velocity, which is higher and comes from a direction inconsistent with a Saturn orbit. So 163 is not the number of grains caught. It is the number that survived a filtering process designed to be conservative out of many thousands of detections. That conservatism cuts both ways. It means the identifications are trustworthy. It also means the calculated infall rate depends on how well the instrument's sensitivity and pointing history were modeled, and there is honest uncertainty in that. Now, the supporting arguments, because the dust measurement was not alone and the case was built from more than one direction. The second line of evidence is the mass, from section 4, and the spreading calculation that goes with it. A ring system loses material and widens over time, and the rate depends on how much is there. Working backward from 0.41 times minus, the rings look like a system that has been evolving for hundreds of millions of years rather than billions. The third is the composition itself. Not just that the rings are clean, but that they are almost entirely water ice with very little rock. If a large mixed body were torn apart to make them, you would expect the rocky component to be there too, and it is not in the proportion you would predict. That is a real puzzle rather than support, and I will come back to it. The fourth is that Saturn's ring system is unique. Section 3 established that Jupiter, Uranus and Neptune all have faint dusty rings, and nothing like Saturn's. If large bright ring systems were a normal permanent feature of giant planets, you would expect to see more than one. If they are rare temporary events, seeing exactly one is what you would expect. Put those four together, and the young ring picture was, for several years, the mainstream position. It appeared in review articles and textbooks, and it was the version that reached the public. I want to close this section with the thing that was always slightly uncomfortable about it, because it was raised at the time by people who accepted the measurement. If the rings formed 100 to 400 million years ago, then something happened at Saturn 100 to 400 million years ago. Something big enough to destroy or dismantle an object of considerable size. in a solar system that had been stable for 4 billion years by that point. The era of heavy bombardment, when large impacts were common, ended around 3.5 billion years ago. By 400 million years ago, the solar system was a quiet, well-ordered place, and it is not obvious what could have happened. So the young ring theory buys you a clean explanation of the ice and hands you a much harder problem about the event. Section 7 is the best current attempt at that problem, and it involves the loss of an entire moon. Before that, there is a version of the young ring argument that does not depend on dust at all, and it is worth having because it survives everything Section 6 is about to do. It is an argument from where the rings are, not what they are made of. The rings sit inside the Roche limit, and they are spreading. Material is crossing the outer edge, and material is draining to the planet. Both of those processes are one way. Nothing is putting material back into the main rings, so the rings must have been more massive in the past, and you can run the calculation backwards to ask how massive. Do that with the measured mass and the measured spreading rate, and the answer is that a few billion years ago, the rings would have had to be enormous. Some versions of that calculation produce an initial ring system, many times the mass of Mimas, which raises its own problems, because a ring that heavy evolves differently and should have left evidence. That is a genuine constraint, and it does not care whether the ice is clean. It is the strongest remaining argument on the young side after Section 6, and it is the one people on the old side have to work hardest to answer. Their answer, broadly, is that the spreading rate is not constant and depends on properties of the ring particles that are not well known, so extrapolating 4.5 billion years backwards from a present-day rate is not reliable. Which is a reasonable objection, and it is also the same shape of objection as the one being made about the dust. In both cases, the argument is that a present-day rate cannot be extended across geological time without knowing more than we know. That is the fifth section. The rings are made of clean ice. Dark dust has been falling into them at a rate measured 1 grain at a time across 13 years, and running those two facts together gives an exposure age of no more than a few 100 million years. That is the case. It is well built, and it was the accepted answer until very recently. Everything in the last section rests on one assumption, and the assumption was never checked. The assumption is that when a dark dust grain hits a ring particle, the dark material stays. That sounds so obvious it barely registers as an assumption. Dust arrives, dust sticks, ice gets dirty. That is how dirt works on every surface you have ever encountered. It is not what happens at 60,000 miles per hour. This is the sixth section, and it covers work published in the last 2 years that has moved the field from a settled answer back to an open question. Very little of it has reached popular coverage yet, which is the main reason it is in tonight's video. You have an intuition about dirt, and that intuition is built entirely from things moving at speeds you have experienced. Dust settling on a shelf, mud thrown onto a car, soot landing on snow. In every case you have ever observed, the dark thing arrives and the dark thing stays, because at those speeds arriving and staying are the same event. None of your intuition covers what happens when the arriving object carries more energy than it takes to destroy both itself and part of what it hits. That is the gap the last 2 years of work has been filling, and it is why the assumption went unexamined for so long. It did not look like an assumption. It looked like a description of how dirt works. Start with what actually occurs at the moment of impact. A micron-sized grain of rock hitting a lump of ice at tens of thousands of miles per hour is not a collision in any ordinary sense. The energy involved is far beyond what holds either object together as a solid. Both the grain and a patch of the ice are converted to vapor, essentially instantaneously. Not shattered, not melted, vaporized, and then further stripped of electrons by the energy of the event, producing a small cloud of charged fragments. This was always known. The cosmic dust analyzer from Section 5 works by exploiting exactly this effect. The instrument catches grains precisely because it vaporizes them and reads the vapor. The question nobody had modeled carefully was what that vapor does next. The young ring calculation implicitly assumed the answer was, it condenses back down and coats the ice. The dark material arrives as a grain, becomes a puff, settles back, and the ring gets a little dirtier with each impact. A team led by Ryuki Hodo, working in Japan, ran the numerical simulations of what happens to hypervelocity impact vapor on an icy target and published the result in Nature Geoscience. What they found is that most of the non-icy material does not come back. The vapor expands outward fast. As it expands, it cools and some of it condenses, but into grains a few billionths of an inch across, rather than a coating. Those grains are electrically charged, both from the impact itself and from ultraviolet light and the plasma environment around Saturn. And a charged nanoparticle sitting inside a planetary magnetic field does not stay where it is. Saturn's magnetosphere sweeps it away, either inward to the planet or outward to space. So the dark material arrives, is destroyed on contact, and is then removed from the system by the magnetic field before it can accumulate. If you follow that chain once more slowly, it is 3 steps, and each one is ordinary physics. The grain is destroyed on impact. What is left is electrically charged. Charged things in a magnetic field get moved. The rings are not being polluted at anything like the rate the age calculation assumed. They are, in the phrase used in that work, resistant to pollution. If that is right, then the cleanliness of the rings stops being a clock. Clean ice is what you would see whether the rings are 100 million years old or 4.5 billion, because the mechanism that was supposed to dirty them does not work. There is a supporting observation for that mechanism which does not depend on any model, and it is the fact that Saturn's magnetosphere is visibly full of exactly the material this predicts. Cassini's instruments found the region around the rings loaded with charged particles and fine grains being transported by the magnetic field. Grains that small streaming outward from the Saturn system were detected not only at Saturn, but by other spacecraft passing at a distance, moving fast enough to have been accelerated by the planet's rotating field. So the removal pathway is not hypothetical. Saturn is measurably flinging fine charged material out of its own system, continuously. What Hyodo's work added was the calculation showing that the impact vapor ends up in exactly that removable form rather than settling back onto the ice. I want to be careful about how strong a claim that is. It does not prove the rings are old. It removes the main piece of evidence that they are young. Those are different statements and the difference matters. There is a way to check the plausibility of this that does not require trusting anybody's simulation, and it is the other icy bodies in the Saturn system. The moons out there are getting the same dust. Some of them are noticeably darker than the rings, which is what the pollution picture predicts. Iapetus famously has one hemisphere far darker than the other, and the leading explanation involves dark material accumulating on its leading face. So dark material clearly does accumulate on some surfaces in the Saturn system. The difference is the impact speed. Dust arriving at a moon and dust arriving at the rings are not hitting at the same velocity, because the ring particles are on fast circular orbits close in and the moons are further out and slower. The vaporization argument is speed dependent, so material can stick to a slow moon and be destroyed on a fast ring particle. That is a consistent story rather than a contradiction, and it is also the kind of detail that needs measurement rather than argument, which is where the field is stuck. Now the second paper, which is from this year, and which goes after the calculation from a different angle. Gregorio Ricerchi and Aurelien Crida published a study in Icarus in 2026, with a title that tells you exactly what it does. It is called a reconsideration of the exposure age. Their argument is about a distinction that had been blurred in the coverage and sometimes in the papers themselves. An exposure age is not a formation age. What the dust measurement gives you, at best, is how long the material currently in the rings has been exposed to incoming dust. That is not the same as how long the ring system has existed, and the two come apart as soon as material is moving. And material is moving. Ring particles are constantly colliding, breaking and reaccreting. Surfaces get buried and exposed. Material drains inward to Saturn, which is section 8. Material spreads outward past the Roche limit. The very small dusty component gets removed by processes operating on timescales of thousands of years, not billions. If the rings are continuously recycling their own surfaces and shedding their dirtiest material, then the ring system can be far older than the exposure age of the ice currently in it. Richerchi and Kreda ran through the assumptions in the original calculation and showed how sensitively the answer depends on them. Change what you assume about how material is transported and buried and lost, and the inferred age moves by orders of magnitude. Their conclusion is that a ring system showing a few 100 million years of exposure could be primordial, dating back to the formation of the solar system. So where does that leave you, if you came into tonight having heard the dinosaur version? Not misinformed. The dinosaur version was the best available reading of a real measurement, published by careful people, and if you repeated it 2 years ago, you were repeating the state of the field. What has changed is that the step from measurement to conclusion turned out to have a soft spot in it, and somebody went and pushed on the soft spot. So where does that leave the field? There are now 2 coherent positions, and I am going to state both as fairly as I can, because you are going to see confident headlines on both sides, and it is worth knowing that neither is settled. The young position says the rings formed in the geologically recent past, from the destruction of a large icy body. The clean ice is a straightforward consequence of the rings being new. The low mass is consistent with a system that has not had long to spread. The uniqueness of Saturn's rings among the 4 giant planets is explained by there being a rare recent event rather than a permanent feature. The old position says the rings formed with Saturn, or shortly after, from material that could never assemble into a moon inside the Roche limit. The clean ice is explained by pollution resistance rather than youth. The low mass is explained by 4.5 billion years of the loss processes in section 8, which means the rings were once far more massive, and we are seeing the remnant. The uniqueness is explained by Saturn simply having had more icy material available in that region than the other 3 planets. Notice that both positions explain all the same observations. That is exactly why the argument has not been resolved. There is one point in favour of the young side that has not been answered well, and it is the composition problem I flagged in section 5. The rings are over 99% water ice. That is not what you get from breaking up an ordinary outer solar system body, because those bodies are typically about half rock. Something has to explain where the rock went. The young theories handle this by proposing that the object destroyed was already differentiated, meaning it had separated into a rocky core and an icy mantle, and that only the mantle was stripped off while the core went into the planet. That is section 7, and it is a specific, testable proposal. The old theories have to explain the same thing over a much longer period, generally by arguing that rocky material is preferentially removed while ice is retained. That is plausible, and it is less developed, and there is a point in favour of the old side that the young side finds genuinely awkward, which is the event problem. If the rings formed a few 100 million years ago, something dramatic happened at Saturn, in an era when nothing dramatic was happening anywhere in the solar system. Nobody has observed such an event at any other planet, and the statistics are unfavourable. So each side has a strong argument and an embarrassment. There is a third position worth putting on the table, because it is where a number of people in the field have quietly landed, and it does not get covered at all. The rings might be old and young at the same time, depending on what you mean by the rings. The idea is a ring system that is continuously recycled. A massive ring forms early, with Saturn, or shortly after. Over billions of years it spreads, drains, and loses most of its mass, exactly as Section 8 describes, leaving a thin remnant. That remnant is then periodically resupplied. A moon wanders in and is torn apart. A comet is captured and disrupted. Material spreads out past the Roche limit and clumps into small moons, which later migrate back in and are destroyed again. On that account, the ring system is ancient as a structure and young as a set of particles, in the same way a river is older than any water in it. That would explain why the exposure age is short while the structure is old. It would explain the small moons just outside the ring edge, which look like they are made of ring material, and it removes the need for a single dramatic event a few 100 million years ago, which is the young theory's weakest point. It also makes Chrysalis in Section 7 one episode in a repeating process rather than a unique catastrophe. I am not presenting that as the answer. It is less developed than either of the other two, and it has the disadvantage of being harder to test, because a model with a cycle in it can accommodate a lot of observations. But it is where the argument may be heading, and you will not have heard it in the coverage. Here is my own honest read, and I am flagging it as opinion rather than reporting. The young ring result was one of the most satisfying stories in planetary science, and I think it travelled further and harder than the evidence supported, because it was a wonderful thing to be able to say. The reversal is less satisfying, and it is going to reach far fewer people. That asymmetry is not anybody behaving badly. It is just what happens when a clean answer becomes a complicated one. There is a question you might reasonably be asking by now, which is why anybody cares how old a set of rings is. It is a fair question, and there are three answers. The first is that ring systems are the only disks of orbiting material anybody can observe up close. Every planetary system in the universe forms out of a disk, and every one of those disks is either too far away to resolve or long gone. Saturn's rings are a working example, running now, close enough to photograph at 500 feet resolution. How they behave over time is the only direct evidence anybody has about how disks behave over time. The second is that the answer changes what you think happened in this solar system recently. If the rings formed 160 million years ago, then a moon the size of Iapetus was destroyed while life on Earth was already well established, and the solar system is a less settled place than it looks. If they are primordial, then nothing dramatic has happened at Saturn since the beginning, and the quiet picture holds. The third is the one that got the coverage. It determines whether the most recognizable object in the sky is a permanent feature or a temporary accident that we happen to be alive for. Those are different kinds of question, and only the third one is really about Saturn. What would settle it is a mission. Sending a spacecraft back to Saturn with instruments designed specifically to measure the composition of ring particles in detail, rather than inferring it from dust caught at range, would resolve the pollution question directly. Concepts for such a mission exist. None is funded and none would arrive before the 2040s. That is the sixth section. The evidence that Saturn's rings are young rested on dark dust accumulating in clean ice, and recent work indicates that the dust is vaporized on impact and swept out by Saturn's magnetic field before it can accumulate. The measurement stands. The clock it was read from may not be a clock. The rings might be 100 million years old, and they might be 4.5 billion, and at the moment nobody can tell you which. There is a moon missing from Saturn, not a moon somebody lost track of. A moon that, if one particular theory is right, orbited Saturn for billions of years, came apart about 160 million years ago, and left the rings behind as the only evidence it was ever there. It has a name, which is a slightly strange thing for an object nobody has ever seen. It is called Chrysalis. That is the seventh section, and it is the best current answer to the question Section 5 left open. If the rings are young, what event made them? Before the moon, you need the problem it was invented to solve, and it is not the one you would expect. It is not the rings at all. It is Saturn's tilt. You already know what a planetary tilt does, because you live on one. Earth's 23.5 degrees is the reason there are seasons. For half the year your hemisphere leans toward the sun, and for the other half it leans away. Saturn has seasons for the same reason, running 29.5 years instead of one, which is why the rings open and close from our point of view, and why spokes come and go. Saturn leans over at about 27 degrees relative to its orbit. That is roughly the same as Earth's tilt of 23.5 degrees, and it is not what you would expect. A planet forming out of a flat disk of gas should end up spinning upright, with its axis perpendicular to its orbit. Jupiter, the largest planet and the one that formed under the most straightforward conditions, is tilted by about 3 degrees. That is close to what the simple picture predicts. Saturn is at 27, and there is no obvious reason. For a while the explanation looked settled, and it involved Neptune. There is a phenomenon in orbital mechanics where two slow periodic motions can lock together. Saturn's spin axis wobbles, slowly, the way a spinning top wobbles, taking on the order of 1,000,000 years for one circuit. Neptune's orbit also shifts slowly, on a broadly similar timescale. When two such motions have nearly the same period, they can capture each other. Small nudges add up in the same direction rather than cancelling out, and the pair locks into step. The proposal was that early in the solar system's history, as the giant planets migrated to their current positions, Saturn's axis wobble came into resonance with Neptune's orbital drift, and that resonance pumped Saturn's tilt up from near zero to its present value over hundreds of millions of years. It was an elegant idea, and it made a specific prediction. If the resonance is what did it, then Saturn and Neptune should still be locked together now, and the numbers should match closely. Then Cassini measured Saturn's interior precisely enough to check, and the numbers did not match. They are close. They are not close enough. Saturn's wobble is near the resonance but not in it. So the resonance may have happened, and Saturn appears to have got out of it, and there is no obvious way to get out of a resonance without something changing. That is where Jack Wisdom comes in. Wisdom is a professor of planetary science at the Massachusetts Institute of Technology, and with colleagues including Burkhard Militzer at Berkeley, he published a proposal in Science in September of 2022. The argument runs as follows. The rate at which Saturn's axis wobbles depends on the moon's. A planet with a lot of mass in orbit around it wobbles differently than a planet without, because the moons pull on the planet's equatorial bulge. So if you remove a moon, you change the wobble rate. And if the wobble rate was sitting right at the edge of a resonance, removing a moon could knock it out. Wisdom's team worked backward. They asked what Saturn's moon system would have needed to look like for the resonance to have worked, and then what would have to change for it to have stopped working. The answer was an extra moon, a satellite roughly the size of Iapetus, which is Saturn's third largest moon, at about 900 miles across, orbiting somewhere between Titan and Iapetus. With that moon present, Saturn sits in the Neptune resonance and gets tilted. Remove it, and Saturn falls out of the resonance and keeps the tilt it already has. They named it Chrysalis, because a chrysalis is a thing that comes apart to release what was inside it. Now the destruction, which is the part that connects to the rings. In the model, Chrysalis was stable for billions of years. Then, roughly 160 million years ago, its orbit was destabilized by interactions with Titan, which is slowly migrating outward. Titan's migration is worth pausing on, because it is a measurement rather than an assumption, and it is one of the more surprising results of the Cassini mission. A moon raises a tide in its planet. The planet's rotation drags that tidal bulge slightly ahead of the moon, and the bulge then pulls the moon forward, feeding it energy and pushing it outward. It is the same process that is moving Earth's moon away from us at about 1.5 inches a year. Standard theory predicted Titan should be migrating outwards slowly, very slowly. Two teams measured it directly, one using Cassini's radio tracking and one using 10 years of astrometry from the spacecraft's cameras, and published in 2020. Both found the same thing. Titan is moving outward about 4.5 inches a year, which is roughly 100 times faster than the standard theory allowed. That result required a different explanation for how Saturn responds to tides, involving resonances inside the planet that amplify the effect. And it changes Titan's history substantially. If it is moving that fast now, it started far closer in. A fast migrating Titan is exactly what the Chrysalis model needs, because a Titan that sweeps outward quickly crosses resonances with other moons and can destabilize things a slow Titan would never reach. So the tilt problem, the ring problem, and Titan's unexpected speed all fit into the same account, and the Titan measurement was made independently and before the Chrysalis paper was written. Once destabilized, the moon's orbit became chaotic, and eventually it made a close pass to Saturn, close enough to cross the Roche limit. At that point, Section 3 takes over. Inside the Roche limit, Saturn's tidal forces exceed what a body's own gravity can resist, and the moon was pulled apart. The model finds that about 99% of the material fell into Saturn. The remaining 1% stayed in orbit, spread into a disk, and became the rings. That fraction is worth stating plainly, because it changes how you think about what you are looking at. If this is right, the rings are not a destroyed moon. They are the small leftover portion of a destroyed moon that failed to fall in. Now, the reason this theory got the attention it did, which is that it solves several problems with one event. It explains the tilt, which was the original problem. It explains why Saturn is out of the Neptune resonance now, despite showing signs of having been in it. It explains the rings, at a date consistent with the young ring estimate from Section 5. And it explains the composition problem I flagged twice already. Iapetus-sized moons are differentiated, meaning heavier rock has settled into a core with an icy mantle around it. In a tidal disruption, the outer layers come off first. Strip the icy mantle from a differentiated moon, and you get a debris disk that is almost entirely water ice, with the rocky core continuing on into the planet. That is exactly what the rings are. Over 99% water ice, with the rock missing. One event, 4 problems, no additional assumptions. That is why it was taken seriously. Now the honest part, because a theory this tidy needs scrutiny. There is no direct evidence Chrysalis existed. It is not a body anybody has observed or a remnant anybody has found. It is a moon whose properties were derived from the requirement that the model work. That is a legitimate way to do science. Neptune was predicted from irregularities in Uranus's orbit before anybody saw it. But Neptune was then observed, and Chrysalis cannot be, because if it existed, it no longer does. The model also involves a chain of events, each of which has some probability attached. The moon has to have existed with roughly the right mass in roughly the right orbit. Titan's migration has to destabilize it. The destabilized orbit has to bring it inside the Roche limit rather than ejecting it or dropping it straight into the planet. Each step is plausible, and the combination is a specific sequence. Other explanations for the tilt exist. Some involve a large impact early on. Some involve the resonance operating differently. None of them explains as many things at once, which is a point in favor of Chrysalis, and also a reason to be slightly suspicious of it, because a theory that explains everything is sometimes a theory with enough free parameters to fit anything. And of course, the whole thing is contingent on the rings being young. If Section 6 is right and the rings are primordial, Chrysalis is not needed to explain them, though it might still be needed to explain the tilt. The two questions are linked, but they are not the same question, and it is worth keeping them apart. It is worth knowing what happened to the idea after it was published, because the reception tells you something. The paper was not attacked. It was received as a serious and careful piece of work by people who then pointed out, politely, that it is unverifiable in principle. That is an uncomfortable category. It is not wrong and it is not testable, at least not directly. What can be tested are its consequences. If Chrysalis existed and was destroyed 160 million years ago, then Saturn's inner moon system should carry traces of the disruption. Some of the small moons should be reaccumulated debris rather than original bodies, and their densities and compositions should reflect that. Several of Saturn's small inner moons do have very low densities, low enough that they must be loosely bound rubble rather than solid objects. That is consistent with the model, and it is also consistent with several other things, so it is support rather than proof. Another consequence is about timing. If the rings and the small moons date from the same event, they should be the same age. There are estimates for the ages of the inner moons based on how much their surfaces have been cratered and how their orbits have evolved, and some of those estimates come out young, others do not. The picture is not clean. So the honest status of Chrysalis is an elegant model, consistent with several independent lines of evidence, unable to be confirmed, and dependent on a ring age that is itself now in question. There is one more possibility that deserves mention, because it is the main competitor, and it is simpler. Rather than a moon of Saturn being destroyed, a large object from the outer solar system, a Kuiper belt body, could have passed close enough to Saturn to be torn apart on a single pass. That requires no missing moon and no chain of destabilization. It requires only that one large body wandered in at the wrong angle. The difficulty with that version is the composition again. A Kuiper belt object is roughly half rock, and unless it too was differentiated and stripped selectively, it should have left a much rockier ring than the one we have. Modeling work on that route continues. One last note on the name, because it says something about how the idea is held by the people who proposed it. Chrysalis is not a formal designation. There is no catalogue entry and no International Astronomical Union approval, because those are for objects that exist. It is a working name for a hypothesis, chosen because a chrysalis is destroyed in the process of releasing what was inside it. Whether that turns out to describe a real moon or an elegant idea that did not survive contact with better data, the name will have been apt either way. That is the seventh section. Saturn's tilt is a real unexplained measurement. The best current explanation involves a moon that no longer exists, and that same moon, torn apart at the Roche limit about 160 million years ago, would account for the rings and for why they are made of almost pure ice. There is no direct evidence for it. It explains an unusual number of things at once, and it stands or falls with the young ring theory it was built to support. Whatever the answer to the age question turns out to be, this section is not in dispute. Saturn's rings are draining into the planet. It has been observed, the rate has been measured more than once by different methods, and the mechanism is understood. Whatever you conclude about the age, you can take this section as settled. That is the eighth section, and it is the one that puts an expiry date on the thing you have been looking at your whole life. You are watching something end. Slowly, on a timescale that makes no difference to you, but genuinely ending, and the process has been measured well enough that you can put a number on it. The process is called ring rain, and the name is close to literal. Here is how it works. In 4 steps, you do not need any physics background for it. Step 1. A ring particle sitting in sunlight is exposed to ultraviolet light, and it is also sitting inside Saturn's magnetosphere, being hit by energetic charged particles. Both of those knock electrons loose from water molecules on the particle's surface. Step 2. A water molecule that has lost an electron is no longer neutral, it has a positive charge. Step 3. A charged particle inside a magnetic field cannot move freely. It is locked to the field lines and has to travel along them. Step 4. Saturn's magnetic field lines run from the ring region down into the planet's upper atmosphere at mid-latitudes, so the charged water follows them down and lands in Saturn's atmosphere as a continuous fall of water. That is ring rain. Water leaving the rings, guided by magnetism, falling into the planet. You can check the plausibility of that chain yourself against something you already know about, because the same physics runs at Earth. Charged particles from the Sun cannot cross Earth's magnetic field lines freely either. They are funneled along them and dumped into the atmosphere near the poles, where they collide with air molecules and make them glow. That is the aurora. The difference at Saturn is where the field lines lead. At Earth, they collect particles from the solar wind and deliver them to the poles. At Saturn, they collect water from the rings and deliver it to the mid-latitudes. Same mechanism, different cargo. The first hint of it goes back further than you would guess, and it sat unresolved for 3 decades. Voyager 2, in 1981, photographed dark bands in Saturn's upper atmosphere at particular latitudes, and one suggestion at the time was that they were caused by material coming down from the rings. That idea sat around for 30 years without confirmation. It was confirmed in 2011, and the confirmation came from an unexpected direction. A team led by James O'Donoghue, then at the University of Leicester, was using the Keck telescope in Hawaii to observe Saturn in infrared. They were looking at a particular kind of glow produced by a charged form of hydrogen high in the atmosphere. That glow is normally spread fairly evenly. What they found instead were dark bands at specific latitudes where the glow was suppressed, and when they traced Saturn's magnetic field lines outward from those latitudes, the lines went straight to the rings. Water arriving from the rings was quenching the glow. The bands were the footprints of the rings, printed on the planet's atmosphere. That result established that ring rain was real. The next question was how much. O'Donoghue and colleagues published a rate in Icarus in 2018. Ring rain alone was delivering somewhere between about 0.5 ton and 3 tons of water per second into Saturn's atmosphere. Take the middle of that range and cash it out, because the number means nothing on its own. At roughly 1.5 tons every second, the rings are losing enough water to fill an Olympic swimming pool about every half hour, continuously, since long before there were people to notice. Nothing you have ever watched drain empties that steadily. And ring rain is not the only lost channel. Separate work using Cassini data from the grand finale, when the spacecraft was flying through the gap and could sample material directly, found additional material draining straight into the equator, in some estimates at a considerably higher rate. Combined figures quoted in the literature run up to around 11 tons per second. There is real uncertainty in these numbers, and I would rather you have the spread than a single confident figure. The low end and the high end differ by more than a factor of 20, but the direction is not in question. The rings are losing mass and nothing is putting it back. There is a second drain that operates on completely different physics, and it is worth understanding because it will still be running long after ring rain has done its work. The rings spread, particles in the rings collide constantly, and every collision exchanges a little momentum. The statistical result of enormous numbers of gentle collisions is that the system slowly widens. Some material creeps outward, some creeps inward. Material that creeps outward past the Roche limit stops being ring and starts being able to gather into moons. That is not speculation. There is a family of small moons sitting just beyond the ring edge, and one leading explanation for where they came from is that they were assembled out of ring material that spread far enough out to clump. If that is right, then Saturn's inner moons are not older than the rings. They are made of ring. Material that creeps inward eventually reaches the planet and falls in, which is the other half of the loss. This process is called viscous spreading, and the word viscous is doing real work. A swarm of colliding particles behaves, over long timescales, like an extremely thick fluid. The rate depends on how much material is present, which is why the mass measurement from section 4 constrains it, and it is slow enough that it does not compete with ring rain on a 100 million year timescale. Over billions of years it dominates, which is exactly the point of contention in section 6. If the rings are ancient, then viscous spreading has been running for 4.5 billion years, and the rings we see are the thin remnant of something once far more massive. That is a coherent position, and it explains the low mass without requiring youth. There is a number in the original O'Donoghue result that is easy to skip past and worth pulling out. The dark bands in Saturn's atmosphere were visible in 2011 data. They were also visible in Voyager images from 1981. 30 years apart, the same latitudes, the same pattern. That means the process is not a recent event or a temporary state. It has been running steadily for at least the entire period anybody has been able to check, and there is no reason to think it started recently. Now the lifetime, which is what everybody wants. Take the measured ring mass from section 4, take the loss rate, divide one by the other. At the higher loss rates, the rings have on the order of 100 million years left. At the lower rates, closer to 300 million. That is the number that gets reported as the rings having an expiry date, and within the limits of the measurement it is fair. 2 caveats, because the calculation is simpler than reality. The first is that the rate is unlikely to be constant. Ring rain depends on how much sunlight is falling on the rings, which changes through Saturn's 29.5-year seasons, and on the state of the magnetosphere, which varies. The rate measured during the Cassini era is a snapshot. The second is that the loss is not uniform across the rings. The inner rings, being closer, drain faster, so the system will not fade evenly. It will erode from the inside outward, and the D and C rings will thin out long before the bright B ring does. What that means practically is that the rings will not vanish one day. They will get thinner and dimmer and less structured over tens of millions of years, and at some point, an observer would stop calling them rings and start calling them a haze. There is a detail here that changes the story slightly, and I think it is the most interesting thing in this section. Ring rain does not only remove water, it is also delivering material to Saturn, and that material is doing chemistry. Cassini's mass spectrometer, during the grand finale, sampled what was coming down in the gap. It did not find only water, it found methane, ammonia, carbon monoxide, molecular nitrogen, and carbon dioxide, along with organic material. That was a surprise. The rings are supposed to be nearly pure water ice, and the infalling material is not. The current interpretation is that the very fine dusty component of the inner rings is chemically different from the large icy boulders that hold the mass, and that it is this fine material, not the ice, that is preferentially draining in. Which loops back to section 6 in a way that is worth noticing. If the dustiest and dirtiest component of the rings is the part being removed fastest, then the rings are continuously cleaning themselves, and the argument that clean ice implies youth gets weaker again. I am not going to overclaim that. The people who work on this are still arguing about how much it matters, but it is a measured composition from a spacecraft flying through the material, and it is not what the simple picture predicted. Something else follows from the seasonal point that you can act on, and it is the reason this section is not purely academic for you. The rings you can see through a telescope tonight are not presented the same way they were 10 years ago, and they will not look the same in 10 more. Saturn's 27-degree tilt means the rings open and close from our point of view across its 29.5-year orbit. At maximum, they are tipped about 27 degrees toward us, and you see them as a wide ellipse. At minimum, they are edge-on and effectively gone. The most recent edge-on crossing was in 2025, so the rings are currently opening again, and over the coming years they will get progressively easier to see, reaching their widest presentation toward the early 2030s. That is a real observing note, rather than a piece of trivia. A small telescope, the kind you can buy for a couple of $100, will show you the rings as a distinct structure separated from the planet. A slightly better one will show you the Cassini division. You are looking at a 3,000-mile gap, cut by a moon 100,000 miles away from it, across 800 million miles of space, through an instrument you can carry under one arm. One last thing about the expiry date, which is about the size of the number rather than the science. 100 to 300 million years sounds like a countdown, and in human terms it is not one. It is longer than the entire history of mammals. The rings will outlast this species by a margin that makes the question of their ending academic for anybody alive now. What the number actually tells you is not about the future, it is about the present. A structure that only lasts a few 100 million years around a planet that has existed for 4.5 billion is a structure you should not expect to find when you look. And we found one, at the only planet we can examine closely, at the exact moment in history when we developed the instruments to examine it. That is either a coincidence, or it is telling us that ring systems are more common and more renewable than they look. Section 3's discovery of rings around Chariklo and Haumea and Quoar leans slightly toward the second. There is one more measurement in this area that deserves stating, because it puts a flaw under everything else in this section. The infalling material has been detected arriving. Not inferred, not modelled, detected. During the grand finale crossings from Section 4, Cassini flew through the gap between the rings and the planet, which is exactly where material draining inward has to pass. 2 instruments sampled it directly, a dust analyzer counting grains and a mass spectrometer identifying molecules. Both found material moving from the rings towards Saturn. The dust instrument registered impacts continuously through the crossings. The spectrometer identified what the material was made of, which is where the methane and organics came from. So the drainage is not a chain of inference from glow patterns in an atmosphere. A spacecraft flew through the falling material and counted it on the way past. That is why I said at the start of this section that it is not disputed. The mechanism is understood, the footprints are visible on the planet, and the material itself has been sampled in transit. The only real uncertainty is the rate, and that is a factor of 20 rather than a question of whether it is happening. That is the 8th section. Saturn's rings are draining into the planet along magnetic field lines, at a rate first inferred from dark bands in the atmosphere and since measured directly, somewhere between 0.5 ton and 11 tons of water every second. At that rate, the rings have between 100 and 300 million years left. That part of tonight is not disputed by anybody. The rings have sharp edges, and they should not. A swarm of hundreds of trillions of independent particles, all sliding past each other at different speeds, has no reason to have a clean boundary anywhere. It should smear out into a smooth gradient, thick in the middle, fading gradually at both ends. Instead, the A-ring stops. The Cassini division has walls. There are gaps a few 100 miles wide, with edges you could describe as knife cut. Something is maintaining that structure against a system that would otherwise blur. And in almost every case, the something is a moon. That is the 9th section, and it is about the small bodies doing the sculpting. Before the mechanisms, it is worth telling you what you would actually notice if you went through this section's features in order of how visible they are to you. The Cassini division you can see from your back garden with a small telescope. The Enki gap needs a good amateur instrument and steady air. The waves Daphnis raises, the braids in the F-ring, the propellers and the spokes are all spacecraft only. You will never see them from Earth, and neither will anybody else. So most of what follows is knowledge you can hold, but not verify yourself. And I would rather say that plainly than let it sound more accessible than it is. Start with the Cassini division, since it is the feature anybody can see and it has the cleanest explanation. The gap sits about 73,000 miles from Saturn's center and is roughly 3,000 miles across. It is not empty, but it holds far less material than the rings on either side. The cause is Mimas, the small moon from section 1 that the ring mass keeps getting compared to. A particle at the inner edge of the Cassini division orbits Saturn exactly twice for every one orbit Mimas completes. That relationship is called a 2-to-1 resonance. What it means physically is that the particle gets a gravitational tug from Mimas at the same point in its orbit, every single orbit. The tugs do not average out, they accumulate in the same direction over and over. Over time, those accumulated tugs stretch the particle's orbit into an ellipse. An elliptical orbit crosses the paths of neighboring particles, which means collisions, which means the particle gets knocked out of that region entirely. So the gap is swept clear and kept clear by a moon 100,000 miles away, doing nothing but passing overhead on a regular schedule. That mechanism appears throughout the rings. Wherever a simple ratio exists between a ring particle's orbit and a moon's orbit, you find structure, a gap, a sharp edge, or a spiral wave running through the material. The spiral waves deserve their own paragraph because they turned out to be a measuring instrument nobody expected to have. At a resonance, instead of clearing material entirely, a moon can set up a wave that winds outward through the rings in a tight spiral. Cassini photographed dozens of them, and each one is named for the moon and the resonance that produces it. The useful part is that the wavelength of such a wave depends on the surface density of the ring material it is traveling through. Measure how the spacing between wave crests changes across the wave, and you can calculate how much material is there. That is how the mass of the A ring and the C ring is actually known, not by weighing them from a spacecraft's trajectory, but by reading density off the waves the moons write into them. There is a further trick. Some waves are driven not by moons but by oscillations inside Saturn itself. The planet rings very slightly, the way a bell does, and those internal vibrations produce gravitational variations that leave waves in the rings. That gave rise to a field with a name that is hard to improve on: chronoseismology, from Chronos, the Greek name for Saturn. By reading waves in the C ring, researchers have inferred properties of Saturn's deep interior, including evidence supporting the fuzzy core from section 4. The rings are being used as a seismograph for the planet they orbit. There is something about that explanation you should push back on, because I glossed it and it deserves better. If Mimas clears the 2-to-1 resonance, why is the Cassini division 3,000 miles wide rather than a thin line? Work published in the last several years indicates Mimas has migrated inward over time, which means its resonance has swept across a range of radii rather than sitting still. A moving resonance clears a band, not a line. So when you look at the Cassini division, you are not looking at a gap cut by a moon in its current position. You are looking at the track of a resonance that has been sliding through the rings, and the width of the gap is a record of how far Mimas has moved. That is worth knowing because it is the general shape of everything in this section. The features are not static furniture, they are the accumulated history of moons that are still moving. Now the moons that sit inside the rings, which are the more dramatic case. Pan is about 17 miles across and orbits inside a gap in the outer A-ring called the Encke gap. It is not near the gap, it is in it. The moon clears the material directly, physically sweeping up anything that strays into its path and gravitationally pushing away the rest. Cassini photographed Pan closely in 2017, and the images caused a small stir because of its shape. Pan has a pronounced ridge running around its equator, which makes it look like a walnut, or the way people usually put it, a ravioli. That ridge is ring material. Pan has been accumulating ice from the gap it is clearing, and because the material arrives in the ring plane, it piles up around the equator rather than covering the moon evenly. Atlas, another small inner moon, has the same feature and is even more extreme. Then there is Daphnis, which is smaller still, about 5 miles across, orbiting in the Keeler gap near the outer edge of the A-ring. Daphnis is slightly tilted relative to the ring plane, and it is close enough to the gap edges to pull on them. As it passes, it raises waves in the ring material on either side. Cassini photographed those waves at high resolution, and the images are the clearest demonstration anywhere of gravity shaping a physical structure. The waves have a measured height, up to about half a mile above the ring plane, on a ring that is otherwise about 30 feet thick. Half a mile of vertical structure on something 30 feet thick, raised by a moon 5 miles across. Daphnis has one more property worth knowing, which is that it is barely holding together. Its density is extremely low, low enough that it cannot be a solid body. It is a loose pile of ice held by its own weak gravity. Sitting inside the ring system, it is disturbing. The same is true of Pan and Atlas and most of the small inner moons. They are rubble, which fits the picture from section 3. These objects are sitting at or near the Roche limit, where Saturn's tides are strong enough to prevent solid assembly. What can exist there is exactly what is there: loosely bound piles that are constantly accumulating ring material and constantly at risk of being pulled apart again. If you wanted a place to watch moons being born and destroyed, this is it, and section 10 has a specific candidate. Next, the F-ring, which is the strangest structure in the system. It is a narrow strand just outside the A-ring, and it is not a simple circle. It has kinks, clumps, and in places multiple strands that appear braided around each other. Its appearance changes noticeably between observations. 2 small moons orbit near it. Prometheus, about 53 miles across, orbits just inside. Pandora, about 50 miles across, orbits just outside. They were called shepherd moons when they were discovered by Voyager, on the idea that the inner one speeds particles up and the outer one slows them down. And between them they keep the ring confined to a narrow lane. That picture is now understood to be too simple. Prometheus in particular is not just confining the ring, it is disturbing it. Its orbit brings it close enough to the F-ring once per orbit to pull streamers of material out of it, leaving channels behind that get sheared into the braided appearance. So the F-ring is not being tidally shepherded, it is being repeatedly damaged and rebuilt, and the structure you see is the record of the most recent damage. Before the propellers, there is a pair of moons out there doing something that sounds like it cannot be allowed, and it is the best single fact in this section. Janus and Epimetheus are 2 small moons, about 110 miles and 70 miles across, orbiting just outside the F-ring. They share an orbit. Their orbital paths differ by about 30 miles, which is less than the radius of either moon. 2 objects on effectively the same orbit, one slightly closer in than the other. The inner one moves faster, so it slowly catches up with the outer one. What happens when it does is not a collision. As the inner moon approaches from behind, the 2 pull on each other. The inner one is pulled forward, which sounds like it should speed it up. In orbital mechanics, it does the opposite. Adding energy to an orbit raises it, and a higher orbit is a slower orbit. So the inner moon rises and slows. The outer moon is pulled backward, loses energy, drops to a lower orbit, and speeds up. They swap. The one that was inside is now outside, and the one that was outside is now inside. They never get closer than about 10,000 miles. Then the new inner moon starts catching up with the new outer one, and the whole thing happens again. The cycle takes 4 years. They have been doing this for as long as anybody has been able to check, and they will keep doing it. 2 moons trading orbits with each other, on schedule, forever. Now the propellers, which are the smallest features that have been detected, and my favorite result in this section, and the one where you get to see something invisible. There are objects in the A-ring too small to see directly. In the range of a few hundred feet to half a mile across, they cannot be imaged, but they are large enough to disturb the material immediately around them, opening a small gap ahead and behind. Those disturbances are visible, even though the object causing them is not, and their shape is a double-lobed structure resembling a propeller. So you are looking at the wake of an object you cannot resolve. In the same way you can see where a boat has been without seeing the boat. Cassini detected thousands of them. The larger ones have been tracked over years, and something unexpected turned up when they were. Their orbits are changing in ways that are not fully explained by the standard picture of how a body interacts with a disk. That matters beyond Saturn, because the same physics governs how planets migrate through disks of gas and dust around young stars. Propellers are the only place anybody can watch that process happening in real time, rather than modeling it. The largest tracked propellers have informal names, after aviators. There is one called Blériot. Now the resupply story, which is the one exception to everything else in this video. Everything so far has been about the rings losing material. The E-ring is the opposite. It is being actively fed. The E-ring is the outermost of the major rings, extremely diffuse, spanning a vast region of space. For decades, its existence was a minor puzzle, because fine particles in that environment should disperse within decades to centuries, and yet the ring persists. Cassini found the source in 2005, and it is Enceladus. Enceladus is a moon about 310 miles across, with a global ocean of liquid water under an icy shell. At its south pole there are fractures, informally called tiger stripes, and from those fractures material is venting continuously into space at around 800 miles per hour. Most of that material falls back. A fraction escapes entirely and goes into orbit around Saturn, and that fraction is the E-ring. Cassini flew directly through those plumes, repeatedly, and sampled them. It found water, salts, silica nanoparticles that indicate hot water reacting with rock on the ocean floor, methane, and complex organic molecules. So one of Saturn's rings is not debris at all. It is the exhaust of an active moon with liquid water and hydrothermal chemistry, and it is being replaced as fast as it disperses. That single fact is the reason Enceladus is one of the leading candidates for life in the solar system, and it was found by a mission that went to Saturn to study the rings and the planet. Enceladus deserves a little more, because if you take one thing from this section, it should probably be this rather than the rings. The moon is small, 310 miles across, which would fit inside the state of Arizona. Its surface is ice, and it is the most reflective surface in the solar system, throwing back over 90% of the light that hits it. The south polar fractures were found in 2005, in the mission's first year, and they were found partly by accident. Cassini's magnetometer registered a disturbance in Saturn's magnetic field near Enceladus that should not have been there for a small, airless moon. That anomaly prompted closer flybys, and the closer flybys found the plumes. There are roughly 100 distinct jets. The material comes out at around 800 miles per hour, which is above the moon's escape velocity, and it reaches hundreds of miles above the surface. Cassini flew through those plumes 8 times. The closest pass took it about 30 miles above the surface, through the spray. What the instruments found, in order of how much it mattered: water, which was expected; salt, which told you the ocean is in contact with a rocky floor rather than sitting in a sealed ice pocket; silica nanoparticles of a size and type that on Earth form only in water above about 190 degrees Fahrenheit, reacting with rock, which told you there is hydrothermal activity down there; molecular hydrogen, which is a usable energy source for life; and large complex organic molecules, found in the data years after the mission ended by people going back through it. That combination is liquid water, an energy source, and organic chemistry, all confirmed by a spacecraft that flew through the material and measured it directly. And the reason you can say all of that is that the moon is throwing its ocean into space and building a ring out of it, so nobody had to land or drill. If you want a single argument for why Cassini was worth what it cost, it is that one. The mission went to study a planet and its rings, and found the most accessible, potentially habitable environment beyond Earth by flying through a plume that also happens to be the E-ring. One more piece of sculpting, and it goes the other way. Mimas is not only cutting the Cassini division. Work published in the last several years indicates that Mimas has migrated inward over time, and that its resonance has therefore swept across the rings rather than staying in one place, which would have shaped a much broader region than the gap alone. And Titan, the largest moon, is migrating outward at a rate that was measured directly using Cassini radio tracking and turned out to be around 100 times faster than the standard theory predicted. That result is what makes the Chrysalis story in Section 7 mechanically possible, because a fast migrating Titan can destabilize things it would otherwise never reach. The moons are not decorations around the rings, they are the machinery that produces every feature in them. If you want one image to keep from this section, make it Daphnis, a moon 5 miles across, which is smaller than most cities you have driven through, moving along a gap in a sheet of ice, raising walls of material half a mile high on either side of it as it goes. You could walk the length of the moon in a couple of hours. The waves it raises are taller than most mountains you have seen. That is what gravity does when nothing is in its way and it has time. There is a general point underneath all of this that is worth extracting, because it applies well beyond Saturn. Every feature in this section is produced by a small object acting on a much larger amount of material over a long time through repetition. Mimas is not powerful. It is a moon 250 miles across, and its pull on any individual ring particle is negligible. What makes it capable of cutting a 3,000-mile gap is that it applies that negligible pull at the same point in the particle's orbit, over and over, for millions of years. Daphnis is 5 miles across and raises structures half a mile high for the same reason. That principle, that a small repeated influence applied in phase will eventually dominate a large system, is the same one that governs how planets migrate through disks around young stars, how asteroid belt gaps form, and how Saturn got tilted by Neptune in Section 7. Saturn's rings are the only place where you can photograph it happening. That is the 9th section. Mimas cuts the Cassini division from 100,000 miles away by tugging on the same particles at the same point in every orbit. Pan and Daphnis clear their gaps from inside them and raise waves half a mile high on a ring 30 feet thick. Prometheus tears streamers out of the F-ring and leaves the braids behind. Objects too small to photograph give themselves away by the propeller-shaped wakes they cut, and the outermost ring is not wreckage at all. It is water being thrown into space by a moon with an ocean under its ice. In 1980, Voyager 1 sent back images of the B-ring with dark streaks across it, running outward from the planet like the spokes of a wheel. Nobody had predicted them. Nobody had seen them from Earth. And 46 years later, nobody can fully explain them. That is the 10th section, and it is about the things still open. Start with what a spoke is, because the shape is the problem. The ring's orbit. Inner material moves faster than outer material, which is the shearing motion from Section 1. Any feature that spans a range of radii should therefore be smeared into a curve almost immediately, because its inner end is outrunning its outer end. A spoke spans thousands of miles of radius and stays roughly radial for a couple of hours before it shears out. For that to happen, the spoke cannot be made of ordinary ring particles following ordinary orbits. Something has to be holding it together, briefly, against the shear. The current explanation, and it is partial, is electrostatic. Spokes appear to be clouds of extremely fine particles, around a micron across, lifted off the surfaces of larger ring particles and held slightly above the ring plane by electric charge. A charged particle above the ring plane is influenced by Saturn's magnetic field as well as its gravity, and the magnetic field rotates with the planet rather than obeying orbital mechanics. That is what lets a spoke hold a radial shape for a while. The strongest evidence for that came early. Analysis in the 1980s found that spoke activity varied with a period matching Saturn kilometric radiation, a radio emission tied to the planet's magnetic field rotation. That is a hard link between spokes and magnetism, and it has held up. What is not settled is the trigger. What charges the dust in the first place, and why in patches, and why then? Two families of explanation compete. One says meteoroid impacts on the rings produce clouds of plasma that charge and lift nearby dust. The other says instabilities in Saturn's magnetosphere periodically dump energetic electrons into the rings and do the same job. Both can produce spokes in a model. Neither predicts the observed pattern well enough to be called correct. A survey of the full Cassini image set, published recently, made the problem sharper rather than easier. It catalogued spoke types that do not fit the standard description at all, including some that appear at radii where the models say they should not form, and some whose shapes are not radial in the expected way. So the count of things to explain went up. There is also a detail about spokes that is easy to miss and worth stating, because it tells you something about the scale involved. A spoke can be 6,000 miles long and 1,000 miles wide, and it is made of particles about a micron across, lifted a few feet above the ring plane. A structure the size of a continent, made of dust, standing a few feet off a sheet 30 feet thick, holding its shape for 2 hours against a system that should shear it apart in minutes. And there is a seasonal element that any explanation has to account for. Spokes are not always there. Voyager saw them in 1980 and 1981. Cassini arrived in 2004 and saw none for 2 years, which was alarming enough that people wondered whether they had been a temporary phenomenon. They reappeared in 2005 and became common again. The pattern that emerged is tied to the angle of sunlight on the rings. Spokes appear when the sun is close to the ring plane, around Saturn's equinoxes, and they fade when the rings are strongly tilted toward the sun. The most recent equinox period brought them back, and the Hubble Space Telescope has been running an observing program specifically to track them. So we have a seasonal, magnetically linked electrostatic phenomenon with no agreed trigger. That is where it stands. There is one detail about the spokes that makes the puzzle personal rather than abstract, and it is about who found them. The Voyager images came down over days and were examined by people working through them frame by frame. The spokes were noticed in raw imagery before anybody had a name or a category for them, and the first reaction in the room was that the camera had a fault. That is a normal reaction to an unexpected feature, and it is worth remembering when you hear that a spacecraft discovered something. The spacecraft returns data. Somebody has to look at an image and decide that a smudge is real. Spokes are not the only open item, and the rest are worth listing plainly. The first is the age, which is the whole spine of tonight. Sections 5 and 6 gave you both cases. It is not resolved, and it will not be resolved by reanalyzing Cassini data, because the argument is now about the physics of impacts rather than about the measurements themselves. The second is the composition problem. Over 99% water ice is a very hard number to produce from any ordinary parent body. The Chrysalis model handles it by stripping a differentiated moon, which works, but requires the moon. Nobody has produced a mechanism that gets you clean ice from a generic captured object. The third is the mass problem in the other direction. If the rings are ancient, they were once far more massive, and a much heavier ring would have evolved differently and left signatures. Whether those signatures should still be visible is argued about. The fourth is the B ring itself, which is embarrassing in a specific way. It holds most of the mass of the system, and it is the one region where the mass is hardest to measure, because the material is dense enough to be opaque. Trying to determine density from how much light gets through does not work when almost none does. Estimates of B ring mass rely on indirect methods and carry the largest error bars in the system. That is a real gap. The most prominent feature of the most studied ring system is the part we have the worst numbers for. The fifth is the propeller migration from section 9, where tracked objects are moving in ways the standard disk interaction model does not reproduce. The sixth is one I have not mentioned yet, and it is the most concrete of them because it is a specific object behaving in a specific way that nobody can account for: Peggy. In April of 2013, Cassini photographed a bright disturbance at the very outer edge of the A-ring, about 750 miles long. The pattern was consistent with a small object, perhaps half a mile across, sitting right at the edge and pulling on the material around it. What made Peggy interesting is where it sits. The outer edge of the A-ring is essentially the Roche limit. That is the boundary from section 3, the line beyond which material can gather into a moon. So Peggy may be a moon being born, caught at the moment of formation, at the exact radius where formation becomes possible. Cassini tracked it for 4 years. It appeared to leave the ring and then, in later observations, appeared to be back. Its behavior was not a clean departure, and it was not fully understood by the time the mission ended. Nobody has looked at it since 2017, because there is no spacecraft there. The seventh is the one that would matter most if anybody could get at it, and it is about the other giant planets. Section 3 established that Jupiter, Uranus and Neptune all have faint dusty rings. What nobody knows is whether any of them ever had a system like Saturn's. If large bright ring systems form and decay repeatedly, then the other three should have had them at some point, and there might be evidence in their moon systems, bodies that look like reaccumulated ring material, orbits that record a disk that is no longer there. Nobody has looked properly, because nobody has been to Uranus or Neptune since the 1980s. Both were visited exactly once, by Voyager 2, on a flyby lasting hours. A Uranus orbiter has been recommended as the highest priority large mission for the next decade by the planetary science community. If it flies, it would arrive in the 2040s, and among the many things it would settle is whether Saturn is genuinely special or simply the one we caught at the right time. That is the question underneath tonight's whole video, and the answer is sitting at a planet nobody has visited in 40 years. Now, what would actually settle any of this? The honest answer is a mission, and there is not one. Cassini is gone, deliberately, in 2017. There is no spacecraft at Saturn now, and none on the way. The next mission approved to that part of the solar system is Dragonfly, a rotorcraft that will fly around on the surface of Titan, and its science is about Titan's chemistry rather than the rings. It is scheduled to launch later this decade and arrive in the mid-2030s. Concepts for a dedicated ring mission exist. They generally involve an orbiter that would spend years inside the ring system rather than passing through it, with instruments designed to measure the composition of individual ring particles directly rather than inferring it from dust collected at a distance. That is the measurement that would end the age argument, because it would tell you how much dark material is actually incorporated in ring particles rather than how much is arriving. None of those concepts is funded. Realistically, a mission launched in the 2030s would arrive in the 2040s, and the answer to the question in tonight's title would come about 25 years from now. That gap deserves a moment of its own, because it is unusual and it is not the field's fault. For 13 years, there was a spacecraft at Saturn producing more data than anybody could analyze. Papers are still coming out of the Cassini archive now, 9 years after the mission ended, and they will keep coming for another decade. But an archive can only answer questions somebody thought to build an instrument for. The pollution question in section 6 requires measuring the internal composition of ring particles, and Cassini was not equipped to do that, because when it was designed in the 1990s, nobody knew that would be the question. That is a recurring pattern in planetary science, and it is worth recognizing. The mission answers the questions of its own era and generates the questions of the next one, and the gap between those two things is measured in decades, because that is how long it takes to build and fly the next spacecraft. Cassini launched in 1997. Anything designed to settle what Cassini raised will not return data until the 2040s. That is a 50-year cycle for one question about one object. There is one thing that will happen sooner, and it costs nothing. Saturn's rings are heading toward another edge on presentation, and the ring plane crossings continue on their 15-year cycle. Around those events, the rings thin to invisibility from Earth and then return. It is the same phenomenon that confused Galileo in 1612, and it is the easiest way for you to see for yourself that this thing is a flat sheet rather than a solid object. And there is one more thing you can do that requires no equipment at all, which is simply to know what you are looking at when Saturn is up. It is visible to the unaided eye, and it always has been. Every civilization that kept records of the sky recorded it as a wandering star, and none of them knew about the rings, because you cannot see them without magnification. So for the entire history of human skywatching up to 1610, people looked directly at Saturn and saw a point of light. The thing that makes it famous was invisible for all of that time, and it has been visible for 416 years. Now let me pull every thread we followed tonight together. The rings are hundreds of trillions of separate pieces of nearly pure water ice, 170,000 miles across and about 30 feet thick. Flat because everything that was not flat got collided into the plane. It took 285 years to work out what they are, from Galileo's ears in 1610 to Keeler measuring the orbital speeds in 1895, with Maxwell proving in 1859 that they had to be particles because everything else was unstable. They exist because they sit inside the Roche limit, where Saturn's tides prevent material from assembling into a moon. All 4 giant planets have rings. Only Saturn's are made of clean ice, and only Saturn's are massive enough to see. Cassini weighed them by flying 22 times through a 1,200-mile gap between the planet and the innermost ring at the end of its life. They came out at 0.41 times the mass of Mimas. That low mass, combined with 163 grains of outside dust caught over 13 years, gave an exposure age of no more than a few 100 million years, and the rings became younger than the dinosaurs. Then that clock was challenged. Impacting dust vaporizes rather than sticking. The charged remains are swept out by Saturn's magnetic field, and a paper this year argues exposure age was never formation age. The rings may be primordial. Chrysalis, a moon the size of Iapetus, torn apart at the Roche limit 160 million years ago, would explain the rings and Saturn's tilt and the missing rock all at once, and there is no direct evidence it ever existed. The rings are draining into Saturn along magnetic field lines at between 0.5 ton and 11 tons of water every second, and they have somewhere between 100 and 300 million years left. Every sharp edge in the system is a moon's work. Mimas cuts the Cassini division from 100,000 miles away. Daphnis raises waves 0.5 mile high. Prometheus tears the Ephring apart and leaves the braids, and Enceladus is actively building the E-ring out of water from an ocean under its ice. And the dark spokes Voyager found in 1980 are still not explained. There is one more thing worth saying before the bottom line, and it is about how to hold a question that does not have an answer yet. You are going to see headlines about Saturn's rings again. Some of them will say the rings are young, and some will say the rings are ancient, and both will be written confidently, and both will be describing real work. The useful thing to carry is not a position. It is the shape of the disagreement. The measurements are not in dispute. The ring mass is 0.41 times Mimas. The dust arrives at a measured rate. The rings are draining at a measured rate. Nobody argues about any of that. What is in dispute is a single step of interpretation, where the dark material that arrives at the rings stays in them. If it stays, the rings are young. If it is destroyed and swept out, the clock does not run and the rings could be any age. That is the whole argument, and it is a question about what happens in the first microsecond after a grain of rock hits a lump of ice at 60,000 miles per hour. An entire debate about the history of the solar system's most famous object comes down to that. So here is the honest bottom line. Saturn's rings shouldn't be there, and that sentence is true in two different ways, and only one of them is settled. They shouldn't be there in the sense that they are not going to be. The draining is measured, and the arithmetic is not complicated. Whether they shouldn't be there in the other sense, whether they are a recent accident that we happen to be alive to see, is a question that looked answered 3 years ago and is open again tonight. I find that better than the tidy version. A clean answer that turns out to be built on an unchecked assumption, taken apart carefully by people who went back and did the impact physics properly. Is science working the way it is supposed to? It just does not make as good a headline as dinosaurs. What is not in doubt is what you are looking at. Hundreds of trillions of pieces of ice orbiting a planet 800 million miles away, arranged into a sheet wide enough to reach most of the way from here to the moon, and thin enough to stand on end in a room, held in shape by moons a few miles across, draining away at a swimming pool every half hour. Older than dinosaurs or older than the Earth, nobody yet knows. Thank you for joining me tonight on this trip out to Saturn. If you found this as fascinating as I did, please take a moment to like this video and subscribe to the channel. It genuinely helps this channel keep making these deep dives into the cosmos. For most of Saturn's history, the planet you can draw from memory did not look like that, and for a while yet, it still does. Good night.